So I'd like to introduce Mr. Mike Thompson from Synopsys right here. Thank you.
All right, hi guys. So I'm going to talk to you today about embedding vision into SoCs. I've been in this business for a while, 35 years or so. I actually focused on microcontrollers and microprocessors, got involved with the 8-bit stuff. Vision is far and away the coolest technology that's come along since I've been involved in this space. The implementation of vision could not have been done even 5 years ago, realistically, into an SoC. I mean, yeah, you could put it in one that drew 100 watts and all that kind of stuff, but I'm talking about something that can be, you have trouble hearing it? Something that could be usable in a real application, especially a mobile application. And you know, has been like little bits of this going on, right? You look at your phone or camera, you go to take a picture and it does framing of faces and things like that. But it's going well beyond that. So I'll talk to you about some of the challenges in vision, so the processors that we just announced, talk to you a little bit about the algorithms, not too much technical detail, but more about what they're capable of doing, some of the tools, and then show you a little bit about an applications that we have. So close your eyes for a second. If you close your eyes, this is about how much input machines have had until now. You know, they can hear. You can touch, right? Now open your eyes. Look at how much richer the experience is. You know, what you can take in, what you can do, the interaction. It's amazing. So computer vision has actually been around for a long time in labs and you know, university campuses, running on large computers, been running on GPUs, especially multiple GPU units for a while. Being able to embed that, though, into an SoC becomes more of a challenge because, one, you're going to be power constrained. And also you're going to be cost constrained, especially if you're looking at putting that out for consumer applications. But you still have to have that level of performance to be able to extract an object from a frame, a video frame. And that actually takes a lot of processing. So this is a very typical vision pipeline. You're going to do, we're going to take the color out of the picture. We don't need color. And actually, when you look, I don't have a picture of it. When you look at how the image gets broken down so that the object can be found, it tends to look like a Picasso drawing, you know. And it's kind of funny because we find, you know, this kind of picture to be very rich. But you look at what can be extracted with a processor, it's actually almost hard for us to find the objects in it. But for the processor, because they're extracting this mathematically, it's much easier if it's simpler. An image pyramid is taking the image and scaling it, so you're going to scale it so the objects are easier to find. And it may be scaled 2, 4, 8 more times, depending. You're going to look for areas of interest, which is what they're doing here. This would be an image scaling. Now, the image ultimately doesn't look like that by the time you get there, but so an area of interest, and then you can see there's going to be probably other areas that are found in that image which, you know, really aren't what you're looking for, so you're going to suppress those. Let's get rid of those and let's focus on what we're actually looking for. So this is a little more depth on what's actually happening in all those stages. Looking at it as 4 blocks makes it look very trivial, but there's a lot of stuff going on. A lot of processing in the background to make this happen, primarily focused on object detection and recognition. We actually use an algorithm called convolutional neural network for the object detection. We do that because the CNN is the most accurate algorithm now. With this processor, we can get accuracies of about 90% across a broad range, the FDDB, or the face detection database library. And by the way, that's better than we can do. So machines, even at an embedded level now, are better than us. At the high end, on ImageNet Challenge, stuff like that, they're exceeding 95%, which is better than human experts. And you look at some of the objects they're detecting, and you know, you look at it real hard and you say, oh yeah, that is. But you have to look at it really, really hard to find it. So it's amazing what can be done with machines today using CNN. CNN also can help us to, do some of the other features here to reduce the amount of processing that we have to do in the rest of the processor. All right, so we introduced the EV52 and EV4. These are vision processors specialized for object detection and gesture recognition. We introduced them in March. And these are based on an ARC, very high performance ARC processor. It's a 10-stage pipeline. You can get that as a dual core, a quad core, between whether it's 52 or 54. It also has a very high performance object detection engine that's specialized for convolutional neural networks. Now that's a completely programmable engine, so you can recognize any object. But it also has a lot of very specialized hardware, so it's very efficient. And what that does, it allows us to combine the efficiency of hardware with the flexibility and programmability of software, which we get over here, and get the best of both to get a very efficient solution for extracting objects from images at good rates of speed with great accuracy, but at very low power consumption and reasonably small size. We also have, and in fact, the performance is greater than 1,000 GOPS per watt, or that's 1,000 billion operations per watt. It's probably not a metric you're that familiar with. We always struggle looking for metrics in the vision space. There really aren't any benchmarks that are, well known or used widely. That's an interesting benchmark because it's really a measure of energy, or performance versus energy. And that's very, very important in embedded applications. We also have full support for the OpenCV and OpenVX programming environments. So the ARC RISC CPUs, again, this is a 10-stage pipeline. We do a lot of the processing on the RISC CPUs. There's a nice balance. So if the image pyramid, the grayscale conversion, that's all done over here on the ARC processors. It's easily programmed with OpenCV or OpenVX using an OpenVX runtime. But then we also have the object detection engine, which allows us to actually extract the objects from the image to recognize them. And then we can pass that information back to the RISC CPUs to put on the color frame or whatever you're going to do, pass that information back to a host processor. By the way, using this scheme, if you're doing like face detection, it doesn't matter in that hardware engine or the object detection engine whether it's one face or 1,000 faces in the image. It takes the same amount of work to extract that information, since we look at the whole image. And it's fast enough that we can track people. You could track an individual around here, but we wouldn't track frame to frame. What we would do is we detect them in every image, and then as we track, we could run something called OpenTLD, track, learn, and detect, and actually recognize that person better as time goes by. The technology is very, very capable, very cool these days. So convolutional neural networks are called a deep learning algorithm. It's often likened to the way our brain works. I think that's really an oversimplification of our brain, even though the algorithm itself is very complex. What it does do, though, is we actually go offline and take like 100,000 images of faces. And it learns. We run an algorithm on that on a big server farm or GPU farm, and it learns what a face looks like, or a hand, or a car, or whatever. And then we can take that information. It creates a mathematical model called a CNN executable or graph. We can take that and then program that model into the object detection engine to take advantage of what it's learned across those 100,000 images to very accurately find that object in other images. So they do, in that sense, replicate how our brain works, because what we do, the way we learn over time, is when you're born, there's probably a little bit of genetic predisposition to recognize a face, but certainly not a smiley face. So over time, we have learned what a face is. So when we look, we're doing a very complex task of recognizing faces, but that's because we've learned what a face looks like over time. CNN can also recognize visual patterns. It's very flexible to light variations, whether the face is this way or this way or this way or even this way. Looking at some of the databases they have, it's interesting how it can find different faces. And you know it's a face because you can see it's a head attached to a body, right? And we would recognize that. But the face, is really sort of obscured, but it'll recognize that type of thing. And by the way, CNN has been outperforming other algorithms, Viola-Jones, SurfSift, all those, for a few years now. At what I call the ImageNet bake-offs. They actually have contests for high-end machines where they look at rather obscure databases of information now and classify things. But they're running, like I said, in the 95% range for accuracy in those big bake-offs now. And this processor is a little over 90%, so it's amazing what you can do. You can see it also supports a very broad range of objects that can detect, face recognition. It can actually be programmed in a way that I would recognize me from you. And by the way, that's an application that's coming very fast into our world. Scene recognition, so you can separate sky from ground, water from sky, that kind of thing. It can tell if you're paying attention, if you're being attentive. It can tell expression. It can be trained for expression. You can do multiple things at once, by the way, and then classify them at the end. It's a very, very powerful capability. So this is how CNN works. Basically what you do is you mathematically look at a small portion of the image, and then it's convoluted in a way that allows it to be refined so that it's easier for the machine to find the object. So it breaks the image down, and this isn't even a good representation of what it looks like when it's finally done. I tell you, it looks like something Picasso drew. It's all messed up and has all this funny gray. It looks really hard for us to recognize what's there, but for the machine it's very easy then. Just keep in mind it's doing it mathematically, but it's done as a successive process. So to do that, we use, again, an object detection engine. This is made up of 2 to 8 processing elements. Each of those processing elements is a 5-stage processor. So it's a very capable processor in its own right, but with very, very specialized hardware for doing the convolutional neural network, or for running that executable to find objects in frames. We then take that, excuse me, it's fully configurable, so you can configure the number of elements. You can configure the streaming interconnect. The streaming interconnect is then dynamically reconfigurable, so you could look for different things in an image in real time if you wanted to. And then again, it's fully programmable, and the whole processor is programmable with C or C++. So it's a very easy environment for the software guys to write code in and use. There we go. So this gives you an idea of some of the capability. Let me walk over here. We look at a number of different resolutions. So this is VGA, right? Which actually is still very widely used in things like surveillance, although we're starting to see a transition to more higher definition image resolutions for surveillance, because they want to look at more things with finer resolution. 720p has become very common. And when you get to the automotive space, 1080p is being used a lot more. You think if your car is going 60 miles an hour and you're looking for a pedestrian, or I like to say baby carriage to make it more dramatic, but or a car, at 60 miles an hour, the car is moving 90 feet a second. It covers a lot of distance in just a little bit of time. So you need that resolution to pick that, whatever it is you're looking for, out. But you can see this is with the EV processor. This, by the way, is the whole processor. The area and the power numbers are for the whole processor, including the memory associated with it. So these aren't nonsense numbers. These are real numbers. Obviously, face detection at 30 frames per second. Very, very low power. Now, again, this is a VGA resolution with just 2 processing elements and less than a millimeter square. And again, that's the processor and everything. You go down here and look at, this is face detection. Now, this is 18 frames per second. A bit slower, right? We're using 8 processing elements, but still just a little over 100 milliwatts of power, and that's running full bore. I mean, think about it, that you're processing 18 HD frames. That's a tremendous amount of data you're jamming through this thing. Finding all the faces in that, in every frame. Okay, and a little over 2.5 millimeters of area. So I mentioned the OpenCV and OpenVX tools. Again, the processor itself is programmed in C or C++. You would use the OpenVX runtime. It's essentially an OS, a Vision OS, that you would build your application in to call the different kernels that you're going to be running to do the object detection. It would call the kernel, for instance. It would know that a kernel for face detection could run on the object detection engine, so it wouldn't try to run it on the RISC processors. It would take advantage of the faster resource that's available. We also have full support for the Open Computer Vision libraries, again, to make it easy to build your application. There you go. So one of the other things we did with the Vision processor is we recognized that this was likely to be used in systems where there's a host processor, perhaps a GPU, perhaps multiple host processors. That's become very common in applications today. So we've designed it in a way that it can be used on its own. There's certainly enough horsepower in the RISC CPU here to do most tasks. So it can be very much used standalone, but it can also be used in an environment with a host processor, GPU, that kind of thing. And it's been designed so that the host has access to the shared memory. It can see what's going on inside of the Vision processor. There's interrupts and a lot of control synchronization that can be done between the host and the Vision processor. So the host really can control the processor as much as it wants, as much as you want, or it could use it completely autonomously and just say, yeah, you go run, and when you have information, tell me. So it's very flexible. This is a face tracker application. As I said earlier, there's a lot of stuff going on. So grayscale conversion. Again, this really trivializes the work that's going on. It's really very complex. This is measure, again, GOPS is billions of operations per second. So you can see just to do the image, the integral of the image takes about 500 million operations per second, and that's on a multi-frame rate. The CNN engine does the object detection. That's in the range of 25-30 GOPS, but it's separate from the RISC processors. You see the detection cascade and some of the other exercises that have to go on in the back end take a lot of power too. But because we have the object detection engine, we can do all this processing in really less than 3 RISC CPUs. So it becomes very capable from a power and a performance standpoint in terms of what you can do with a processor. All right, this is just a rehash of that information. This is the area and the power. This was done with 4 RISC CPUs. We only needed 3, but you could actually, at synthesis time, take one of them out if you really didn't need it in your application. And just 2 processing elements in the object detection engine. So we could have put more elements in there if we wanted to do this at 60 frames per second, for instance, to increase the performance. Very capable. Okay, this is a summary. So the vision space, like I said, is one of the most, if not the most, it's certainly one of the most exciting areas right now in the electronics industry. I really believe that looking 10, 15 years from now, we'll see this as being a very strong shift in the way we interact with electronics and it interacts with us, really in our world. As vision gets introduced and that capability becomes real in electronics and then the products that we use. I mean, self-driving cars are coming. I was just reading online here, and somebody's putting out an oven that recognizes the food you put into it, and it cooks it appropriately. That might be a little bit overkill. I'm still okay with pushing buttons, but maybe my kids aren't.
You want me to do that?
But you can start thinking of the applications that you can do when machines can see. It's really a powerful capability. Now, to put this in perspective, 15 years ago, actually 16 now, in 1999, Intel, AJ works for Intel, introduced the Pentium 3 at 488 megahertz. That was state of the art 15 years ago. What's this look like in 15 years? 2030. This is cool. This is really cool. This is an exciting time to be alive. So we've introduced the vision processors. These are very low power. They're targeted entirely for embedded applications. So to be integrated into an SoC, we're talking to people that'll integrate it potentially into a GPU, for instance, because it has better capability for the processing of vision than the GPU itself. Very low power, very small size, again, targeted vision applications. If you want more information, hopefully that's the next slide, yeah, you can get it off of our website, which is not here. Let me click this and see if it is here. No. So, or you can send me an email, just mtho at Synopsys.com. All right, questions?
Any questions for Mike? Or you can stick around and talk to him
Happy
after.
to talk to you.
The Synopsys IP catalog is all located on the ChipEstimate.com website as well, along with their videos, their white papers, and technical newsletters. And
A lot of
so
information.
it's all there. It's all there. So stick around. We're going to be giving some raffle tickets for a drawing later on in the day for an iPad Mini. And if you'd like to pick up one of our mugs, just take your ticket. So they've gotten one? Okay. And just take your ticket over and show it to the gal at the Nicole at the front desk here, and she'll give you a nice ChipEstimate.com mug. Thank you, Mike Thompson from Synopsys.
Thank you, guys.